To do is go through problem 6-1. First, anybody have any questions about chapter 6-1 at all? This is autocorrelation. And I'm going to put the definition up. I want to do some problems, and then I'm going to put some PowerPoints up and show you what you're responsible for. Now, autocorrelation functions are or really cross-correlation more so, but autocorrelations give you a lot of information and the spectral density in the spectrum, the frequency domain about a function. So in general, if you have a process x of t that is what they call wide sense stationary. Now, if you look on OneNote, I put up about, I think, four PDFs that are PowerPoint based, and they're lectures by a guy named Chan, and I forgot the other person's name, that detail this in a very compact way, what you need to know, why you need to know. So first of all, if x of t is wide sense stationary, in other words, it doesn't matter when you, remember the dice rolling business and all that? So if you sample this thing at any point in time, the statistics of it are the same. They don't vary versus time. That's the whole idea of this. If you've got x of t that's wide sense stationary and you want something called the autocorrelation function of x, and it will be a function of tau. Here tau is just going to be defined as t2 minus t1. It is the expected value of x of t times x of t plus tau. And if you look at that, that's really in the limit, these are for power signals, as t goes to infinity, it would be 1 over t integral from minus infinity, this is the fundamental definition of x of t times x of t plus tau times dt. So fundamentally, you're taking a function, multiplying it by itself, and then integrating it technically over from minus infinity to infinity to get the value. That's all it is. And I'm going to go through this kind of quick. I hope everybody had a chance to look at this. I'm going to do the problems at 4, but I want to get this out on the board because this is something, the last bit of stuff. Now, if you look at this right here, what that is, if you look at Rx of 0, what that is the expected value of just x of t times x of t, or that is the expected value of simply x squared of t. Now remember, that's wide sense stationary. What is the expected value of x squared of any random function? I mean, if we have a random variable, always. It's called what? The mean squared value. Do y'all remember that? So this is actually going to be x squared bar. It's just, it will always be equal to, or it'll be either greater than or equal to the value of the autocorrelation anywhere. That's the first thing. The second thing, now this is the first thing that's important. So if you take an autocorrelation function and evaluate it at tau where the time separation is 0, you get the mean squared value. You all with me? The second thing is the mean value, and put down mean value can be found this way. If you let in the limit as tau goes to infinity of Rx of tau, now you have values of x of t and x of t plus tau separated as far as possible. Are you all with me on this? And what that really is going to give you is the DC component. It's called the average value of a signal, but it's the squared. So this is the expected value squared of x of t. And what we call that normally is x bar squared. Are you with me? The first thing I showed you was the mean squared value. That is the square of the mean. Just take a moment. If you didn't read through this, I'm hitting the high points as quick as I can. You all with me? Now, if you look at this, the third thing you can gather from that is, and I want to say one thing about this too. If you have a signal that is like say x of t was cosine of omega t plus some random phase angle, the phase angle is uniformly distributed from minus pi to pi, you'd find that the autocorrelation function will have an a squared over 2 times cosine squared of omega tau. Just go with me on this one, all right? Now, a cosine waveform or a sine waveform can't be evaluated in the limit because they're continually oscillating, right? But they do have a mean value. So if there are periodic components that are repetitive in and out of correlation, this will not give you the true mean here. This is one of those cases where you got to be careful. Periodic functions, and I'll put Rx tau, will not give correct mean. All right. Finally, the third thing is straightforward. If you want the standard deviation of the random process that this autocorrelation function is given by, that's just equal to x squared bar minus x bar squared, just like before. Yeah.
Variance?
What? That is the variance. This is the variance, right? Did I say, sorry, standard deviation squared, the variance is given by that. It's just as before, right? Nothing's important about that. I'll go through the PowerPoint too briefly, but I want to just say this so everybody gets, these are the things that you have to understand. If you take a look at Rx of tau, and you would plot it versus tau. Remember, tau, the only thing you care about is the difference in the 2 time points. It doesn't matter if it's T1 is 100 and T2 is 101, or T1 is 1,000 and T2 is 1,001. It's the difference, statistical difference, because this is Weissen's station. You're always going to get the maximum value possible there. But it could, if it's a repetitive process, this will be equal to or greater than any other maximum. So if it's a periodic process, you could get something like this. And there's some things in there. So this would be a peak, and they're always even functions too. That's another important thing. This is a possible autocorrelation function. And I'm just going to say typical autocorrelation functions for most, not all, most things look like this. Most spectrums that are based on actual measurements, like in radar, we use this stuff, but we do cross correlation. We send a signal, then we store that information, we get a signal back. Y'all with me? Then what we do is a cross correlation. We would take x of t times x transmitted of t times x received of t, and we'd look at this. And the correlator will give you, where it's a peak, will tell you how far away the target is. That time difference is equal to twice the total. I mean, it's basically equal to 2r. If the signal goes out to r at the speed of light and comes back because it's reflected, the total distance traveled is 2r. If you divide that by c, that value of t is what tau will be in the actual it's really the cross-correlation function. And a lot of times we do that in the frequency band. I'm just throwing a lot at you, but I'm telling you, this is something I use, frankly, all the time. Or at least maybe not all the time, but most of the time in the radar course, this is a very important part. So here's a typical autocorrelation function. First, it's an even function, it's like that. That would be something, the shape, it's symmetric, the peak value is going to be when tau equals 0, and I'm plotting versus tau here, so this is tau equals 0. And you'll notice it's symmetric, and there are no vertical parts to that. That's an impossibility. I want to make sure I say this. And I have slides. Did anybody look at the slides I put up about this? If you didn't, I'm trying to underscore the facts. So this is an impossible autocorrelation function. If you had something like this, no. You can't have vertical sides. And the reason is mathematically shown. If you go through here, this has to have a smoothly varying, it can't be discontinuous. It can't if this is used. Y'all with me? There's mathematical proof. You can't have that. Also, for this thing, the peak has to be here. If you had a function like this, that's not a legitimate autocorrelation function because the peak is somewhere else besides tau equals 0. Y'all with me? And finally, I'm showing you these things just to make you aware of some problems because when you're writing code, this is the one thing I found, and you probably know it too. You write code, if you blindly believe the results and don't have any kind of sanity checks, You get information, and all of a sudden you get peaks out there, you get all sorts of things that are prohibited, but if you're not aware they're prohibited, you're going to use that information to get further information, and everything's based on the wrong premise. That's one thing you got to be aware of. It has to be symmetric. So an autocorrelation function like this would not be allowed. It has to be an even function. Y'all with me? And it can never be negative. All right? It can't be negative. How many have had autocorrelation or cross-correlation or correlation in general in other courses? Other courses, not this one. No? Didn't they do any of this stuff in labs? Physics? No? Where did you do it? Which class?
I used it at my co-op.
Oh, no. Co-op is different. We're talking about in the classroom. Now, frankly, because I don't know, and it may depend on who you have. In mathematics, a lot of times, they'll cover some of this stuff. Didn't you have basic statistics in some course? Don't you get business course, like business law or something? Don't you take economics or something?
Yeah, engineering. Is it engineering economics?
Engineering econ?
Yeah.
Well, that has to have correlation, doesn't it?
I don't know.
Are you serious? They
We
don't?
learned about the present value and future value of money. Yeah.
We learned about money.
That's it. Linear
There we go.
information.
All right, I won't draw that comment. Anyway, these are important things. I'm just taking the highlights of this stuff. Go ahead, what? I want to do 6-1.1. I'll move out of here quickly. Now, if you haven't done it, just be aware. As a matter of fact, my reader is right here. So I'm going to do it, and I want to show you something about this. These are things that I'm saying you're responsible for, the final exam, but I'm literally telling you it's a fastball, and I'm throwing it at the lower corner, outer corner of the plate. So you know exactly what's coming.
You want the exercise or the
No,
exam?
problems 6-1.1. That was assigned, correct, class?
Yeah.
All right, this is 6-1.1, and I'm going as fast as legally possible.
6. Those are exercises.
Chapter 6-1.1. It's the first
Oh,
problem.
6 is long. Okay.
I wish we had more time. We were cut by 3 lectures. Do you realize that?
Yeah. Sucks.
Stationary random process having sample functions of big X T has an autocorrelation function of Rx tau equals 5e to the negative 5 absolute value of tau.
Yeah, and this, you gotta make sure, see that absolute value, that makes it even. If it wasn't, it would grow in the other direction, in the negative. Go ahead.
Another random process has sample functions of y of t equals x of t plus b times x t minus 0.1.
Now, that is an absolute value. What I'm going to do is call this alpha and make alpha equal 0.1, just so you get a handle on it. That's fixed, not variable. You all with me? So now I want to show you something. Please be attentive. If I can get your attention here, I'll be very happy. Now, we've got the autocorrelation of that. We want the autocorrelation of that. So that's the expected value of y of t times y of t plus tau. You all follow me? I'm just putting a literal definition of that in there. With me? When I do that, one of these days we're going to get some markers. Always work. All right, when I do that, but I end up getting, and now I would tell you this, don't be in a hurry to do this, just literally replicate this function, y of t here. And so now I have x of t, right, plus b times x of t minus alpha, alpha's a constant. Still may get a good mark.
This is find the value of b minus the mean square value of y.
Yeah, and that's what we're up to right now. So we have this times, and now I have to add tau. So now I have that, and then I have x of t plus tau. This is a bit tedious at times. It's bookkeeping plus b, and it's going to be x of t minus alpha plus tau. Is everybody with me on this? I'm just literally putting in the definition of y of t and y of t plus tau. Now I'm gonna go ahead and square it out. So now I have the expected value of x of t times x of t plus tau and then I'm gonna have plus, now I'm trying to do this in a way you can see it. Now I'm gonna have b squared, right? I'm doing the last one now. B squared times the expected value of, and now it's gonna be x of t minus alpha times x of t minus alpha plus tau. And now I'm gonna get twice, well, I'm gonna go ahead and just do this so you can see. Now it's going to be plus x of t here, well, x of t times this, so it's the expected value of, and it's going to be x of t times this one, which is times b, I'll put b, b times x of t, right, times x of t plus tau minus alpha, and finally plus b times the expected value of x of t minus alpha times x of t plus tau. And let me take b out in front of this one, and you'll understand what I'm doing. Okay? Can you all follow me what I did?
Yeah.
I'm just, now, the next part, I'm going to talk my way through, but I'm going to try to be clear. This is just more or less bookkeeping at that point. There's nothing tricky. And the solutions are there. He does not go through this lengthy process. That's the problem. You don't see all the steps. You with me? Everybody? All right. Now look here. What is this? That's the definition of the autocorrelation function, isn't it? So I'm just going to put that down here so that it's R, sorry. This is Rx of tau. That's all it is, right? Do you all agree with that? Now look at this one. It's plus b squared. Now I want you to notice something. What is the difference in these two arguments? You all see this, if we replace t with, say, t prime here, we get x of t prime times x of t prime plus tau, right? Remember, it doesn't matter where this function begins and ends as long as the difference in the two time points is the same. This right here is the autocorrelation function, all right? Because adding or subtracting any value to this, if you could, you can, I don't have the definition of autocorrelation. Let me put it up here. If you look at Rx of tau, the definition is the expected value of x of t times x of t plus tau, right? Now, the only thing you care about is the difference in these two times, which is tau, right? So if I add plus 1 to this one and plus 1 to this one, it does nothing. You all with me? That's my point. So this right here is the autocorrelation. So it's really Rx of tau here. Now, I'm trying to be clear about this. You agree with that? All right, plus.
Is that supposed to be like a bigger x? Or is that the same size x? Rx?
Well, it just means it's a function of x. That the autocorrelation came from the random process defined here. Just not defined mathematically, it's a random process. That's the autocorrelation function. That's all it means. Has nothing to do with y. If it was Ry of tau, then it would be, that's what we're going to get. That's what we're getting here. This is going to be Ry of tau. And that's what we're going for. You all with me?
Yeah.
James, are you okay with that? Or not? What do you have a question on? You're looking like.
No.
You okay? You're good with that, Ken? All right. Now what about this one? Remember what I just said, time difference?
We just did that.
We just did that one.
Oh, I'm sorry, this one. Well, this one is t. This one is tau minus alpha, right? Isn't the difference in these two arguments just tau minus alpha?
Yeah.
All right, that you can place as the argument Rx of that argument. It's just the time difference of the two, right? So if you look at this one is plus B, and this would be Rx of now. This one is going to be tau minus alpha, right? Y'all follow me?
So,
If you look at what tau is, if you want to know what tau is, you take this argument and subtract this argument from it and take an absolute value. Y'all with me, class? Everybody? Finally, what about the last one? You tell me. What's the difference?
T is minus tau.
Just subtract them. What do you get?
So would it
You
be?
get either minus alpha plus tau, right?
Yeah.
Or tau minus alpha. Either one is going to be the same because it's an even function. So it's going to be Rx of tau minus alpha. And we know alpha in this one is 0.1. I'm just showing you the method, right? Bradley? What's
I
wrong?
thought you subtracted, so.
What do? You're looking at
plus
the
tau
difference.
minus tau.
Take this one and subtract that one, or take this one and subtract that one. The t goes away, small t, right? What's left? It's either going to be
Tau, oh, okay, tau plus
Well,
alpha or
just,
tau
here,
minus.
I'll tell you what, let's do this. Take t minus alpha, we can do it this way, maybe I'm wrong. Minus quantity t plus tau, what do you get? So it's minus alpha, I guess you were right, it's going to be minus tau. So it could be, this is actually plus here. It's the difference, right? It can be plus, my bad, you're right, brother. You're right. But that's the way you do it, you subtract the arguments. All right. This is the function, this is the technical autocorrelation function for R of y based on the autocorrelation function for R of Rx, for x, right? Now he asked us to find the value b that minimizes the mean squared value, right? What is the mean squared value? What is tau for the mean squared value?
0.
Y'all hear that? You got that? So make it equal to 0. Now what do you get? I'm going to come up, I'm going to erase this, and I'm going to use this board. I'm trying to get through this as quickly as possible. So what happens here? If Rx is 0, remember we want the value that's going to minimize or maximize? Minimize the autocorrelation, right?
Minimize.
Huh?
Minimize.
All right, so let me do this. For the first one, I'm going to have Rx of 0, right, times 1 plus b squared. Now the only thing I've done here, I factored Rx of tau here, let tau equal 0, and I have 1 plus b squared as a coefficient. That's all I'm doing. You with me, class? You look at me like I don't believe. Sometimes I don't believe myself. What about this one? Tau is 0, what do you have? This is going to be plus what? Plus b times Rx of, if tau is 0, it's just going to be of d. It doesn't matter if it's minus d or plus d. Alpha, pardon me, alpha. That's this one here. Do you all agree? Yeah. Tau is 0. Tau is 0 over here, right? It's going to be plus b, right? And it's going to be Rx of alpha. Do you all see this?
And that'd
I mean,
be
it doesn't
minus
matter.
alpha. Your middle one is minus alpha.
Doesn't matter. It's an even function. Like, look. See this? If tau is minus alpha or plus alpha, it's the magnitude. Do you all see this? Let me make that point. Rx of minus alpha is the same thing as Rx of plus alpha if it is a legitimate autocorrelation function. And this one is, just look, right? Okay, so can't I make this twice this? That's what I'm going to do. All right, next, think back. How do you always find the minimum or maximum of a function, the
Take the
derivative, and set it equal to?
0.
0, right. If we take the derivative on this side, what do you get? Well, I'm going to get Rx of 0, right? And it's times 2b here, correct? Y'all agree with that? Just take a derivative. This one is 0, this one is r's at 0, 2b, and it's gonna be plus what? 2 times rx of alpha, right? Alpha's 0.1 in this one. I mean, do you remember this stuff, doing this kind of problem? You remember autocorrelation? Didn't you have
On the
autocorrelation?
topic, but I didn't have time to cover it.
I mean, with Bashir, didn't he do that?
I'm
He
saying-
should have gone into detail. This is a very important thing. And radar, really cross-correlation is what we live on, but we look at the autocorrelation of signals we send too. So if that's the case at equal to 0, what do you notice about this? I can take this to the other side. They got the wrong answer in the book on this one, and just put it equal to minus that. Do you agree with that?
Yeah. We got the solutions.
What?
I think we got the solutions still.
I did. Didn't I post them?
The email never went through.
Yeah.
What?
That's why I don't email
That
you
email you
about.
sent in class, you did it never went through.
Yeah.
We never-
But take a look at chapter 601 now. Isn't the solutions there?
No,
Please
but-
send me an email. I thought it was up.
All the PowerPoints are there.
I will put up the solution. I thought I posted it.
No, that's what I try to email you about.
Okay, look guys, what happens now? Y'all see the two goes away? I'm gonna send it to you in 1 second. What happens now? B is equal to Rx of 0.1, right? That's what alpha is. It's minus this over Rx of 0, correct? What is that? Just take a look. Well, if I look at Rx of 0.1, that's 5e to the minus 0.5, right? So that's 5e to the minus 0.5 over 5, correct? Because when tau is 0, that's 5, correct? 5's go away, and you get a minus there. This is the right answer. It's minus e to the minus 0.5. Now, that's the first part. I'll show you, I'll send you the solutions in 1 second. What's the second part?
Find the value of the minimum mean squared value of y of t.
Find the minimum value?
Yeah, find the value of the minimum.
Well,
mean
the only
squared
thing you're
value.
gonna do is what? That's the value of B that makes it a minimum, right?
You plug it in.
Right? And they want the mean squared value. That's when tau equals,
0.
follow me? So the only thing we're gonna do is take this and evaluate it at 0. That's 5, isn't it? Correct? What is this? B squared times 5, right? Or you can take 5 times 1 plus B squared, and that's B squared over there. What's this? Tau equals 0, it's B times, really, I put it up there. It's this one, right? That's 5, that's 2 times B, that's B. This is Rx of minus 0.1, right? Let me show you, I'll just show you this on MathCAD real quick, and we'll do the next one. How much time do we got? I'm trying to move through here, but I'm trying to just cover this, then I'll cover your questions. Now, I should think section 4-4 is pretty straightforward, and let me put up the solutions too. I want to get this out of the way. I've been doing a lot of stuff. I had the defense yesterday, I had all sorts of other crazy stuff come out of the woodwork on me, evaluating code. When you plug in that value for and it should be minus actually. You're gonna get the same thing, but can y'all follow me on this one, class? All right, so this is gonna be the value, the mean squared value. Yeah,
I would open up the email you sent and only still on the website.
you're kidding me. All right, hold on. The second part was just evaluating y of tau when tau is 0, that's it. Y'all follow me, class? So if we have the function y as a function of tau, we just put tau equals 0. That's all we had to do. Finally, the last part of that problem is what?
If absolute value of b is less than 1, find the maximum mean squared value of y of t.
All right, now what I did was this, and I just want to make sure you see this. You can see this is a plot for y as a function of b. Y'all with me, class? You can see that the minimum value, did I get it here? Is going to be somewhere about here, right? But they say from -1 to +1, I think, are the limits, right? So I could take a derivative of this with respect to b and set it equal to 0. Do you all follow me? And I could find the value of b. But I'm just telling you that's how it would be done. I plotted it. Are you with me? All right, now the next part for that, do you all get the solutions?
Sure. Yeah.
All right, now take a look at the next part. What does it say? The next problem.
Which problem? 2?
6.1-2.
For each of the autocorrelation functions given below.
Oh, good. Let me get this up, because this is a good one. And we're going to talk about is it or is it not wide sense stationary. Wide sense stationary means that the value of the function is only a function of the difference in the two time points. The problem is it doesn't have to be symmetric according to his definition. Technically, it should be an autocorrelation function, which means it should be an even function. Some of these aren't, but he's going to say they're wide sense stationary. So this one, let me see if I can get that. All right. Oh, that's not the book. Give me the book. Please be attentive to this one. So this is problem 6. All right, this is the second problem. For each of the autocorrelations given below, state whether the process represents wide sense stationary or cannot be wide sense stationary. Now, there is a possibility it's wide sense stationary for some of these if the time interval, T1 and T2, is greater than 0. Do you all hear me on this? However, in the technical sense, it isn't. Some of these aren't. Now, if you look at this one right here, can you all see this right here? Can you not see this? That is really e to the, it's going to be e to the minus quantity T2 minus T1. Do you all see that? All right, that is a difference in time, so technically it possibly could be wide sense stationary. That's actually not, because it's not magnitude of that. You all see this, class? If you have a value of that, that would be tau T2 minus T1. If it's negative, then it becomes a function that blows up. So even though it is possibly for some limiting factor, it's really not. This one is different. Do you recognize that trig identity? That's cosine A minus B. I don't know if you remember that. Cosine A minus B is cosine A, cosine B minus a minus or plus sine A, sine B. That one can be, because if it, and he does, in his solutions, doesn't he have cosine of T2 minus T1 or T1 minus T2? You see it?
Where?
6 dash,
For the solutions?
yeah, James is going to look at it. It's there. All right, now you all see that could be a cosine of either T2 minus T1 or T1 minus T2, but cosine's an even function. So in fact, that is wide sense stationary. See it, James? No. Dash 1.2.
He says it could be, yeah, it's cosine T1 minus T2.
Yes. All right, now what about the next one? You tell me. Now I want you to look not at the solutions, but look. Can you now factor that? See how the argument is T1 squared minus T2 squared? Please take a look at that. You could factor that as what? T1 minus T2 times T1 plus T2, right? Well, that's not just a function of T1 minus, but it's also a function of T1 plus T2, no. It should say no or something like not wide sense station. Isn't it?
Yeah.
You with me, guys? I got one more to do after this. Finally, the last one. Now, this is kind of tricky. You remember sine A plus B? Sine A plus B? That's what? Sine A times cosine B minus cosine A sine B. These are tricky identities, but it is. So this would be what? A sine of T1 minus T2, or T2 over T1 minus T2. What do you call that function? What is sine x over x? Anyone?
C.
Yeah, SIM with a C, right? It's a sinc function, it's even, yes, in fact, we'll have a maximum when the difference in the two is 0. That can be, and he should say that. Why, possibly, it says, why it's possibly mind sensitive. I don't even know his words on this one. But do y'all agree? All right, now, just watch me here. I'm gonna get right to the point. Here's the one I wanted to get at. It's not the section, but I want to ask you questions. Remember what I said were legitimate. And the answers to this is 6-3.1. It really belongs in the first section. Now look at this. Which of these are legitimate autocorrelations? You have to look carefully. Tell me about this one. Why not? You're right.
It's a straight line.
It's not a symmetric function. It's not an even function. Do you all see that, class?
Yeah.
What about this one?
Yes.
No.
Why not?
No,
because
straight
it's
line.
discontinuous.
It's discontinuous. Can't be.
It's vertical.
Look at the solutions first. Can you get that, James? All right, now, here's where your eyes have to be clear, and this is not done there. That isn't minus 2 exactly. He skews it. That is 2. Y'all follow me? You can't tell by looking. If this goes to 0 less than minus 2, and this goes to 0 at 2, is it or not?
No.
No, why?
Because it's not even. It's
not symmetric. It's not an even function.
Yeah, not symmetric.
Now, doesn't he say that? Are you looking at the solutions or not, James?
That's what he said.
6-3.1. I promise you this is it. What?
It's not an even function.
It isn't. What about this? Just ask, why
I
not?
have 2 peaks.
Well, you can have 2 peaks, but
You
what's,
can't have a peak on the negative side.
at tau equals 0, it is not a maximum.
Yeah.
All right, and these things sort of showcase the legitimacy of this. I'm not going to do this one, but this one, the autocorrelation from this one right here is going to be basically y squared cosine, or y squared over 2 cosine squared of omega naught, and this would be tau there. I'm not going to show you how to do this one right now, because frankly, we don't have time. Now, the next thing, we're done with problems. Now, hopefully, I can get to the thing I really wanted to. So now, the power spectral density, this guy, I'm using him. Okay, it's a straightforward thing. And I think I posted this. If you have some random process, I didn't ask you this, but how do you get the mean value if you had an autocorrelation function? I'm going to step over here before I get done. And I had an autocorrelation function like this. Rx of tau is equal to, say, 5e to the minus 5 magnitude of tau plus 2. How do I find out what the mean value is? Not make it plus 4. Well, in the limit, right, as tau goes to infinity of Rx of tau, what you're going to get is the mean value squared. You all follow me? Can everybody see in the limit as tau goes to infinity, this goes away. So 4 would be the mean squared value. Do you all agree with that? Square root of that is plus or minus 2. You don't know the polarity, just the magnitude. That would be the mean value. Yeah.
You said, 4 is the mean squared value,
Yes.
not the mean value squared.
The mean value squared. Mean value squared. Sorry.
Right.
Guess I'm trying to go too fast. All right. You agree with that?
Right.
Wow.
So earlier we wrote the mean squared value.
Is tau equals 0.
It's tau equals 0.
Yeah.
Oh, this is the limit as tau goes to, okay.
All right. Y'all follow me on that?
Follow.
And the reason is because that has to be the DC component. If you have a value of the function at, say, x of 0 and then x at infinity and you multiply them together, if there's no oscillatory function, then the only possibility is you got the DC component. That's it.
Oh.
So, now, back to this. I really hate to do this fast, but we got to cover this. You need this for your comms, I think, course. Nobody's here to comment. Because you're gonna get it this fall, some of you, with Chandra, and he is big on this kind of stuff. He's an information theory expert, he's world-class. All right, so next, and I show the proof in a paper there, if you want the power spectral density, technically, if you take the value of the function, now this is just fundamental. I know you guys, when you think of power, you think of resistance, it's 1/2 V squared over R and stuff. Here, we assume the resistance is 1. Just go with me, consider X of T a voltage. But this is the sort of general definition of power. It is proportional to X squared if X of T is a functional form. When you look at this, it's 1 over 2T from minus T to T. Usually it's just 1 over T from minus T over 2 to T over 2. That's the definition. If you have a random process, the power spectral density is the expected value in the limit as T goes to infinity of 1 over 2T minus T to T of X of T squared dt. Now I've got a question for you. What is the power spectral density of any signal that is time limited or finite amount of energy? Think about it. I got a DC pulse of 1 volt that exists from -1 to +1 seconds, right? V squared, 1 squared times the width 2, right? Divided by T or 2T as T goes to infinity is 0. Do y'all follow me? That's a very important point. Y'all with me? Okay. Now the power spectral density is the expected value of that over 2T. And you know how to do a Fourier transform. So what I'm going to tell you is, and I'm going to just say straightforward, if you want the power spectral density, and this is, I never read the whole theorem. In grad school, I took some advanced classes in this stuff. Einstein-Wiener-Kirchhoff theorem. All right, really, only thing you have to know is you want the power spectral density, take the Fourier transform of the autocorrelation function. That's it. And that'll show you something. But that is so important. We do this with radar work all the time. I don't have time to get into it today. So this is a simple example. I've got Rx of tau is e to the minus 2 alpha tau. Now for that to be, that value of alpha could be anything. Y'all with me? The Fourier transform of that is just 4 times alpha over 4 alpha squared plus omega squared. Got a question for you. How would you figure out the DC value from this frequency response? What would the DC value of the power spectral density be at omega equals?
Well, it had to be 0.
Omega equals 0, it's what? 1 over alpha. Do you see that? All right, 1 over alpha. That is called, that would be squared value of the power spectral density. It says, what that says is there is a DC value. Y'all follow me on that? A DC value for this signal. This is an interesting one. Oh, I'm not going to go there. Let's see. He gives some examples. And don't worry, some of this is a little advanced. Don't worry about questions. Now, let me see if I can get on OneNote. This is what I've posted. He goes into wide sense stationary too, and I want to say that wide sense stationary is basically going to say the same thing. This u of x of t means the mean is a constant. If you have an x of t function, the mean has to be a constant. You know how to evaluate the constant, right? Right? Now, remember that cosine, I mean, when we have periodicity, the problem is if the autocorrelation had a cosine, say omega t, cosine squared of omega t variation, it does this the whole time, right? It's oscillatory. It doesn't have a value that becomes a constant. Do you all see that? And that means it is not wide sense stationary. We'll talk about that more later. Technically, there's ways around that, but don't worry about it. Frankly, that's the only thing I'm going to mention there. And I did that. I think I did it. Now, we can go back. Did you have questions about anything in in section 4-4.4-4? Anybody? Did you have a question?
I can't think of one.
Okay. Can nobody think of one? Okay, let's do your quiz. All right, because can you do me a favor, get behind this guy right here?